Welcome to today's lesson on a library of functions. As always, fast forward to the section that you need to look at the most. We're going to start off by looking at linear functions. And linear functions are really just straight lines with, instead of a y, we have f of x. So all we're doing now is replacing y with f of x to basically point out that we're now dealing with a function rather than just the graph, right? Y equals mx plus b is just the graph of a straight line. F of x equals mx plus b is now the function. Well, they're technically the same thing, right? If you graph this, you're going to get the exact same graph as y equals mx plus b. If you plug a value into the function, you'd get the same answer for y as if you plugged a value into the line. So the only real difference is kind of the theory behind it. When we're talking about a function, it's now supposed to be something that is modeling a phenomenon in the real world. So that's the only difference. Is we're just trying to show that these things can be used to model real life things. So here are some typical examples of graphs, and just reminding us of what it means to have a positive slope, right, versus a negative slope. Something that has a horizontal slope or a slope equal to 0, and then a line that goes through the origin at a 45-degree angle. That's going to be your slope of 1, and that's going to be the function y equals x, or in this case f of x equals x, right? So every value of x, you get the exact same answer for y. When x equals 3, y equals 3. When x equals negative 2, y equals negative 2. Here's an example. The megatooth specimen. We can calculate the length of a shark it came from by using a very simple formula. The length of the shark is equal to 0.96 times the height of the tooth minus 22. You'll hopefully recognize this as y equals m, x, and b. Right? So it's a straight line. In this case, our slope is 0.96 and our b is negative 0.22. So that just means if the height of the tooth were 0, right? If we plugged a 0 into this, the answer would be negative 0.22, or the length of the shark would be negative 0.22, which is kind of silly. And that's because these are now functions modeling real world things, so they might not necessarily work for all values of x, right? They're only going to be accurate over a certain interval. With this particular example, with the 15.6 centimeter tooth, when we plug that in, we get a shark that is almost 50 feet long. On to important properties of functions. Increasing and decreasing and constant functions, it's often important and helpful to realize when our functions are increasing and decreasing. There's going to be a lot of symbols thrown at you here, so just try and latch on to the ideas and don't get bogged down in the symbols just yet. So increasing just means as you move from left to right, the function is getting taller, right? So for any x that's further to the right, you're going to have an f of x value or a y value that's also further up. Again, don't get hung up on all of this junk. Just understand what it means to be increasing. And the most basic idea is that it just gets bigger, right? As we move to the right, it goes up. It's that simple. And then decreasing is a no duh. As we move to the right, it goes down. Again, don't worry so much about the syntax, just understand the idea of it. Constant functions, of course, are those flat lines that we're used to. And the big thing is going to be we can have functions that do all three. Right? This particular function is a piecewise function, and it's defined differently over each interval. But you can hopefully see that over the interval negative infinity to 2, the function is increasing. Now I know you might think it's decreasing because this arrow is pointing down, but that's just showing that this function goes on forever, right? We could keep writing it. But as we move from the left to the right, what's happening to the function? It's coming up, right? It's getting taller and taller, so that's increasing. And then on this interval here, it's constant. And then on the green interval, it's decreasing. A relative minimum of a function or a relative maximum of a function are just points that are, for a minimum, the smallest, and for a maximum, the tallest, in a certain neighborhood. Again, don't get worried about the specific definition. Just make sure you understand the idea. And the best way to do that is to look at a picture. So these are relative mins and maxes, right? Even though this height is not the highest point on this entire function, it is the highest point in this neighborhood, right? So that's why it's a relative maximum. It's the highest point relative to a neighborhood around it. Just like this is not the lowest point, but it is the bottom of the trough, right? So you're basically looking for tops of peaks and bottoms of troughs, because this ends up being the minimum in this neighborhood. This is the overall maximum and the overall minimum. So they'll start talking about, you can have a relative max and you can have a global max. You can have a relative min and you can have a global min. And the global just means it happens to be the biggest, right, maximum if we're talking about a global max. And if we're talking about a global min, it happens to be the actual smallest number possible. But any global is also relative, right? This is still the maximum of its little neighborhood. This is still the minimum of its little neighborhood. It just happens to be the ultimate smallest one, right, and the ultimate biggest one. Even functions just means that anytime you plug a negative number in, you're going to get the same answer as if you plug a positive number in. One of our more, I hate to use famous, but the ones we like to look at a lot is just the simple function y equals x squared, which we're now going to call f of x equals x squared. That's an even function because this is true for all x's. Plug in -1, you get -1 squared, that's the same as 1 squared. Plug in -2, you get -2 squared, which is 4, which is the same as 2 squared, and so on and so forth. And if you were to graph it, well, that's just a horrible picture. It's supposed to be symmetrical, right? This distance to here is the same distance to there. So anytime it's symmetrical around the y-axis, that's when you know it's an even function. An odd function, kind of like the name says, is the opposite of an even function, where this time when you put a negative number into the function, you get the opposite answer out of it that you would have from the even number, or sorry, from the other number, from the positive. So if I put -2 in there, the answer is going to be the exact opposite of what I got for 2. Now that doesn't mean that the answer has to be negative, it just means that it has to be the opposite. So if you had, let's say, 2 goes to 4, 3 goes to -6, and 5 goes to -4, let's say, then in order for this to be an odd function, -2 would have to go to -4, -3 would have to go to 6, and -5 would have to go to +4, right? So it just has to go to the exact opposite number. That's what an odd function is. Graphically speaking, odd functions have symmetry with the origin, or if you can think of it, and it's kind of hard to visualize, but they're symmetrical around the line y equals x. Next, we want to evaluate and graph piecewise functions. We've already seen one in this lesson. A piecewise function is basically just a combination of functions that are all graphed together at once. Here's an example. We have this function f of x, and it's defined two ways. It's defined as x squared whenever x is less than 1, but then it's defined as 2x plus 1 whenever x is greater than or equal to 1. What you want to do is start plotting points, or if you're familiar with what the functions look like, you can just start graphing them on their intervals. This particular example, they want you to evaluate two specific numbers, right? They want you to figure out what f of 0 and f of 2 equal. Well, in order to evaluate f of 0, you have to figure out which interval it's on. And 0 is less than 1, so f of 0 has to go into the top function, and you square it and get 0. F of 2, however, is greater than 1, so it's in that second interval, so you stick that in the second function, and 2 times 2 is 4, 4 plus 1 is 5, and that's how you get those answers for just evaluating a piecewise function. If you want to graph a piecewise function, you need to just graph each piece. And all you have to do is take your interval, right, your xy axes, and break them up into these two pieces. So this function changes at x equals 1. So the left-hand side, less than 1, graphs as this. So now you can pick a couple points and graph the line over here. And since it's a straight line, we know we only have to graph 2 points to figure out what it is. So I'd let, I'd go over here very simply and do x, y, and say if x is 0, y is 1. And let's go ahead and pick 1. It's always a good idea to figure out what happens at the limit, where the things change. So let's pick 1. And 1, we plug this in, we get negative 2 plus 1, negative 1. Alright, so 0, 1, and then 1, negative 1. And it's going to be an open circle. And again, bad drawing skills, but you get the idea. Why is this an open circle instead of a closed dot? And it's because it's a strictly less than. So now we move on to this one. Again, let's start with the line here. Plug in 1 and we get 4. So it's going to be up here at 4. And it's a solid dot because this one isn't equals. And then we can just, 2 is very simple. So that's going to be 7. It's going to be up here somewhere. Again, I can't draw to save my life, but you get the idea. There is your piecewise function graphed. This is just talking about what we just did. Talking about graphing the second piece of it. And then, of course, their picture, much better than mine. And that's all you have to do, is put the two pieces together on one graph, and you now have graphed a piecewise function. The greatest integer function, a tough function to understand. The best thing to do is to look at the graph. This is the greatest integer function. You can see that, and let's just look at one interval. Let's look at the interval from 3 to 4. Okay. So when x equals 3, the function equals 3. And as x is a little bit bigger than 3, the function stays at 3 until we get to 4, and then it's going to jump up, and if we continued this, there'd be the dot at 4, and then the line would keep going. So look at another one. Look at this interval over here. At -1, right, we're at a height of -1. But as we get a little bit smaller, all of a sudden it jumps down here. So the greatest integer function graphs out as the biggest integer that is smaller than whatever number you give it. So if you give it 2.5, the biggest integer that is still less than 2.5 is 2. And that's why 2.5 maps up to a height of 2. Right? If you give it negative 2.5, what's the biggest whole number that's smaller than 2.5? Well, this one's a little trickier to conceptualize, but it would be negative 3, right? Because when we're in the negatives, it's kind of in the other direction. So negative 2.5 gets mapped to negative 3. And then as we get bigger and bigger and bigger, it stays there until we finally get to negative 2, and then it jumps up. So the greatest integer function just looks like stair steps. Last but not least, we can look at some basic functions and how to graph them. The best thing to do is to kind of get familiar with families of functions, what's called here libraries of functions, but you can think of them as a family of function or a grouping of functions, functions that have things in common. We should know what all constant functions looks like. They're just horizontal lines at some height c. We should know what all linear functions look like, right? And know something about their symmetry, that the domain is all real numbers, the range is all real numbers, etc., etc., etc. You should get to know what the square function looks like, or basically, even more generally, you should get to know what ax squared plus bx plus c looks like, a quadratic, which looks like this. They just are wider or narrower or shifted and things like that. If a is negative, it opens down, right? All those types of things. So get to know these properties, but try and generalize them. Instead of thinking that the range is always 0 to infinity, that's only true for this basic case, right? For the more general case, this is not always true. It's whatever the vertex is. You could have a quadrilateral that looks like this, and now all of a sudden your range is from 8 to infinity. Or you could have one that's negative and opens like this over here, and now all of a sudden your range is from, let's say, 2 down to negative infinity, right? So try to learn the more general cases rather than these specific simple ones. X cubed looks like that, the cubing function, or the odd powered, right? And then x to the fifth, x to the seventh, they're all going to look basically this same shape. The absolute value function, recognize it as the v. Square root function looks like half of a parabola on its side. And then the cube root function looks just like the cubed function, but flipped, right, on its side. See? 1 over x. And anytime you have x's or functions of x on the bottom of a fraction, that's where you always have to worry about dividing by 0, and you're going to get vertical asymptotes. In this case, the vertical asymptote is the actual axes, but we could have 1 over x plus 1, and now all of a sudden the vertical asymptote would be over here at negative 1, right? Because that would be the problem. If x equals negative 1, then you'd have 1 over 0. There's the greatest integer function. We've already seen that. So we'll end on this slide because this function is a lot more important than the greatest integer function. That's it.